Hello everyone, welcome. I'm going to talk about macOS security today. I will reveal two vulnerabilities I have found and show how to defeat macOS using either of the two vulners. My name is Duozhi Fan, a security researcher from at Security Lab. I started learning macOS security from about the second half of year 2019. To be honest, I'm almost a newcomer in this field. On October 10th, 2019, I submitted my first vulnerability to Apple. It was fixed on December 10th. Then I especially posted a Twitter to market, and this is the first time I participate in a security conference as a speaker. Thank you for attending my talk. There are three keywords in my talk: extended file attribute, compatibility, and defeating macOS. That's the agenda of my talk today. And what is extended file attribute? This is a concept in file system. File system is a huge subject. I will not discuss the details of file system today. I will focus on the vulnerable part, the implementation of extended file attribute. For brevity, I will use XATTR extended attribute or just attribute instead of extended file attribute in the remainder of the talk. They are both the same thing. About extended attribute, let's see an example. We usually use Finder to manage our files. There are many interesting features in Finder. For example, file tags. In Finder, you can mark a file with a color tag. You can assign a red tag to a file and a green tag to another file. You can also customize some text tags by yourself, as shown in the figure. Then, if you try to sort or group files by tags, files with the same tag will group together. This is more in line with your personal preferences than sorting by file name. This feature seems to be powerful. How to implement it? For normal users, file consists of file name and its content. But from the perspective of file system, files have a rich meaning. Besides file name and data, it also contains other attributes such as file size, access time, and owner. And also there are some advanced attributes. For example, file tags. Obviously, they can't be stored in file content. File system allocates new storage space for them, called extended file attributes. But how to view and operate extended attribute? Well, macOS provides several commands to do this. For example, mdls and xattr. Let's use the xattr command to check the file and marked with the red tag before. We can find that there is an attribute named item user tags. I noticed that the attribute content has a BP list header, which looks much like a plist file. We can dump the content into a human-readable XML file through following commands. You can find a string with the content red6 in XML. Okay, that's the reason. The Finder will display a red mark next to the file based on this information. So, how exactly is ATTR implemented? After all, every feature in the system should be implemented by code. The answer is macOS provides a series of XATTR system calls, such as get and set XATTR. We can use the following code to test whether it is the same as we thought. Set an attribute named the item user tag to the file to make Finder think that the file is marked with a red tag. I just reuse the XATTR content dumped from the previous red tagged file, and then assign this piece of binary data to the file through the set XATTR syscall. It turns out that, yes, we can indeed get a file with a red mark, so the set XATTR syscall works. Okay, I noticed that macOS supports many file system formats. Refer to the disk utility application. you can see HFS plus and APFS. These two are Apple's private file system. There is no doubt that they support XATTR. But I noticed that there are other file systems, FAT and EXFAT. Do these support XATTR too? I created a disk image formatted with FAT32, then mounted the image and create tagged files in it. Successful. Color tag has appeared. The answer is yes. However, FAT is a very old file system which only provides basic file management functions. Intuition tells me that XATTR is definitely not supported. There must be some black magic behind it. Fortunately, XNew, the macOS kernel, is open source, so we can analyze how the FAT file system supports XATTR at the code level. XATTR syscalls are implemented in the following C source file, vfs.xattr.c. When we call set xattr, all the arguments will be passed to VNOP set xattr. Each file system driver will register a callback function in vnode operation, that is VNOP. For APFS, the corresponding VNOP will do the write set xattr operation. But for FAT file system, the callback function just returns an error, which is error not support, indicating that the XATTR feature is not supported. And then the following code path will be executed. A function named default set XATTR is called. By reading the code, I found that for file systems that don't support XATTR natively, like FAT, Apple uses an extra hidden file prefixed with ._ to simulate XATTR. That's where attribute data store in FAT file system. Anyway, we can now conclude that the FAT file system itself doesn't support XATTR, but Apple introduces Apple double file, which implements a compatible layer. Why should Apple do this compatible layer? I guess that this may be due to user experience considerations. Users may be confused if some features are unsupported on other file systems. Use a regular file in user space to simulate XATTR. That means file parsing in kernel. File parsing is actually a difficult thing. There are thousands of CVEs all about file parsing. For example, DOC, PDF, image, audio. There have been many CVEs in history. The Apple double file also follows a certain file format and requires file parsing. Are there vulnerabilities in it? The format of the Apple double file is very simple. It mainly stores key value pairs. And though the file format is simple, there is still a chance to find some flaws in its implementation. Fuzz testing is an effective way to find the file parsing vulnerabilities, but Apple double file parsing is processed in kernel. We must customize a unique fuzzing tool to do this, which will take a lot of time. And because the file format is relatively simple, its parsing code is a few hundred lines of code. So I chose code audit, which is sufficient. The layout of Apple double file is shown in right. Several types of data are stored in sequence. First is Apple double header, then extended attribute header, then the attribute keys, and finally attribute values. When I did the code audit, I saw this function, check and swap attribute header. It is responsible for verifying the Apple double file, confirm whether the file structure is legal. This for loop is used to check if the stored key value pair is in a valid data area. But look at this line marked in red. It does two things, add offset and length, to see if there is an integer overflow and check the end of attribute data and see if it exceeds the end of the data area. However, this code doesn't check the offset itself. It must be located in the valid data area too, that is between data start and data end specified by the header. When offset is less than data start, attribute data will overlap with the previous data structure, such as struct ample double header or struct attr header. This is not a big problem when get xattr reads xattr. At most, it reads some unexpected data from the file header. However, when calling set xattr to set attribute, here comes the problem. It is equivalent to a write operation, and all these overlapping data structures can be modified. This is the vulnerability I want to talk about, the vulnerability in extended attribute. We must take advantage of this corruption to do some useful things, such as arbitrary memory read and write, controlling PC registers, and so on. Then I started to read the code, search all the code related to these two headers to see if there are any useful side effects. Of course, I'm lucky enough. I found something very useful. First, I found this piece of code. When set xattr operation is completed, the corresponding changes will be saved to the xattr file. The save operation is completed by write xattr info. Before writing the file back to disk, the file size will be recalculated because when a new xattr is added or a longer xattr is set, the file size may change. The new file size is calculated by data start plus data length. Referring to the previous page, these two fields are within the coverage of the illegal entry offset. I can change any of them to increase the size of the file. Increase the size, for example, to 64 megabytes or 64 MB. Write xattr info will follow our instructions and write the same amount of memory to the file. The problem is, in fact, the ample double file in the memory generally only allocates 64 kilobytes of memory. The write file operation is actually equivalent to a memory copy. If we ask to save 64 MB, and then the wanted length is greater than the real length, an out-of-bound read occurs. The content of the memory after xattr info page will be faithfully saved to the ample double file. And this file, of course, is readable and writable by the user space, so we can use this to disclose kernel memory information. Here, I dump 64 MB of kernel memory to xattr file and display them in hexadecimal. The green mark is an illegal offset I forged, pointing to the data start field in file header, which can be achieved by tampering with the dot_ prefixed xattr file in user space. Data bytes starting from file offset 64 KB or hex 10000 is the kernel memory we read out of bounds. So what can we do with the OB read? Everybody knows that modern kernels ASLR protection is enabled. That is address space layer randomized. We can use the memory disclosure to inspect kernel memory layout, useful to bypass ASLR. Actually, I put an IPC key message after xattr info page in advance, referring to the definition of a key message. When there is only one key message, both prev and the next pointer point to itself, which is the first address of this key message. Through this trick, we can calculate our location in kernel. So now ASLR is not a problem. Just to mention, self-location by IPC key message, a common exploitation technique, is dead in the latest version of kernel. Okay, now we have an OOB read, but this is not enough for kernel privilege escalation. Usually, we need an arbitrary kernel memory write to achieve this goal. This is the most challenging point of this vulnerability. I will explain in detail. Since I can now control the data in the two headers, I continue to look at the code and check if there are other useful side effects. I noticed the following code. Before and after write xattr info to file, there is a swap AD header operation respectively. This function does something relatively simple to perform a swap operation on some integers in the header. That is converting byte order of some integers. Why is there a swap operation there? This is because ample double files are stored in big endian order, and x86 is a little endian CPU. So the data in the memory here is inconsistent with the byte order in the file. Data or integers cannot be written directly to the file. Byte order conversion is required. So before writing the file, there is a swap AD header operation to do this. Back to this function, there is a for loop. The loop count comes from the header, and we can modify the data in the header arbitrarily. So we can control the loop count of the for loop. Next, we can turn the loop count into a very large number, such as 1 million, and the for loop will be continuously. And then we get an out of bounds. However, this is not an OOB write, it is just an OOB swap. What can OOB swap do? Here I must introduce the OOB timestamp vulnerability by Brandon Izzard. Brandon proves that even an OOB write that cannot control memory content precisely can also finish a successful attack. Similarly, the OOB swap cannot precisely control the memory content too, but I will use Brandon's technique to complete the exploit. If you swap an integer as the swap AD header did, but still interpret the integer in little endian, the value of the integer will change. So if you can make a number bigger or smaller, for example, hex 123 to hex 4321 becomes a bigger value, that's enough. I will make an RPC key message bigger than its original size. First, I place a key message after the xattr info memory page. This key message is the target of our OOB swap. The field in the first of the key message header is AKM size, which is an unsigned int 32. Because key message has a variable length, this field is used to record the length of a key message. When it is going to be released, the allocated memory is freed according to this AKM size. If we use OOB swap operation to make this field bigger, such as hex 1234 to hex 4321, then if we release this key message, we will actually release more memory than expected. And the other key object following this key message, I put an OL pause here, will be released together. But the reference to the following key object is still here. We can still use the released object. That is, we get use alter free. Finally, we can convert the OOB swap vulnerability to a very useful type of vulnerability. However, in the process of my research, one detail was overlooked. The OOB swap operation continuously swaps 12 bytes or 3 uints at a time. and the starting position is not aligned to 4 bytes. Therefore, we cannot swap only the IKM size field. In fact, what we get is a 10-byte out-of-bounds swap marked in green. I got more side effects than I originally expected, and the worst thing is that these side effects are harmful to my exploit. Let's see this figure. The first three fields of IPC key message, IKM size, IKM flags, and IKM next are cropped. Especially the lower 2 bytes of IKM next come from IKM flags. IKM next, a very important pointer, which is corrupted and everything is messed up. Of course, we can still control the size of IKM size and trigger the overfree operation successfully, but the kernel panicked immediately. According to the panic information, I found the following code. The kernel will do some checks before releasing key message. We must ensure that IKM next is valid. Trouble comes one after another. Let us observe the result of OOB swap again. The higher 16-bit of IKM flags cover the lower 16-bit of the IKM next pointer. In most cases, the higher bits of IKM flags are zeros, so it can be approximated that the lower 16 bits of IKM next are cleared to 0. So how do we avoid this panic? Consider such a situation if key message is allocated at address aligned to 64 KB. For example, address hex 12340000. Thanks to IKM next points to key message itself. IKM next pointer equals hex 1234000002. That is, the lower 16 bits of the IKM next pointer are zeros, and this time, even if OOB swap clears its lower bits to 0, it is still a valid pointer. Because its lower bits are originally 0, so that harmful side effects can be eliminated, and we can get a perfect UAF. To achieve this, allocate IPC key message on a 64 KB aligned address, which ends with 4 zeros. We must control the layout of the kernel heap precisely. I did the following work. Note that all these operations are performed in the kernel map, not zone memory, because OOB swap occurs in the kernel map and is on an x86 CPU. The memory range, the memory page is 4 KB. I allocate many key messages with 17 pages size continuously, which means that the size of a key message is hex 110000. What's the advantage of doing this is that the address of these key messages will increase sequentially. Well, we only care about the changes in the lower 16 bits. Their addresses are hex 1000, 2000, 3000, and so on. Okay, I can get a 64 aligned key message marked in red. Remember what we mentioned in the OOB read part. I can read a large amount of memory after XATTR info is written to user space. So I can clearly know which key message is I want. And then I will split the key messages and show in the figure below to the heap pages I want. I need to release 3 continuous key message starting from 4 zeros, and then reallocate 4 memory blocks, 1 16-page block and 2 8-page blocks. The rest of the memory is merged into the next key message, a 19-page block, which is no specific effect, just fills up the memory hole. This 16-page memory block is reserved for XATTR info. It is aligned to 64 KB now. The next 8-page memory block will also be aligned to 64 KB. Put a key message at this location, which is the candidate object, and will be corrupted by OOB swamp. Then, in the next 8-page memory block, I put an OL pause page, which is our overfree target. After these operations, I will make the IKM size from 32 KB to 46 KB through OOB swap, and then release the corrupted key message. Now we get a perfect UAF on OL pause page. In fact, we still have another problem. Here again, another new problem. Look at this code again, and I find that after the XATTR file is saved, there is a swap back operation immediately. The memory will be restored to its previous little ending state. In other words, our overfree operation must occur during the write file stage. Maybe we can do this with a risk condition. Let's create two threads. The first thread performs set XATTR and OOB swap things, and the second thread waits for the right moment and destroys the key message, i.e. trigger overfree. It must be done during the write file stage. There is a problem here. We have no way to detect when OOB swap has occurred and when does it end. And so it is not easy to determine when to destroy the key message. A syscall usually costs only a few microseconds, so the suitable time window is very small. Then what should we do? Fortunately, write file is an I/O operation, which is very time consuming. Moreover, we can control the size of the XATTR file. So I chose to save 64 megabytes of memory to the XATTR file. Then the set XATTR syscall will expand to tens of milliseconds. In this way, our time window is relatively sufficient. The strategy is as follows. First, calculate the time required to dump 64 MB of memory in OOB read state. Second, launch a second 64 MB dump and do the OOB swap. In 1/3 of the time, destroy the key message in other thread. Then overfree is made. At this time, the set XATTR thread is still busy writing XATTR file. Everything happens too suddenly. Okay, now that all the problems have been solved, we can put these steps together and to perform a complete exploit. I split the exploit strategy to two parts. Part 1 is the main exploit, and part 2 is post-exploit. I will not discuss the details of the exploit process. You can find the exploit code in my GitHub. The link is given in the bottom left corner of the page. And now we have the arbitrary kernel read-write ability over. However, in the latest OS, TLP0 is no longer accessible. But anyway, we have many ways to achieve arbitrary kernel read-write. That is not a problem. What we need most is a vulnerability as a starting point. Now let's talk about KEXC. Since this is an x86 CPU, there is no protection such as back. So find a suitable kernel object and forge a virtual function. Then trigger the virtual function from user mode. You can achieve the goal of kernel code execution. I will not expand it here, and in most cases, you can already escalate it to root by arbitrary read-write. Usually this is enough. Only in some special scenarios, we need to call the kernel functions. So KEXC is not that important, as Brandon mentioned before. Compared to macOS, many people are more concerned about iOS. After all, iOS has a larger number of users, and the usage of the device is always limited. Unlike Mac, you can't get root permissions through normal operations. People need to exploit to take full control of their iPhones. And then let's talk about the impact of this vulnerability on iOS. The conclusion is that iOS is not affected. Although iOS and macOS share the same kernel code, there are still differences in implementation. iOS has commented out the XATTR compatible code. iOS has introduced a new mechanism to support the Files app Finder on iPhone, that is UserFS. UserFS implements the support of external file system in user space. When you plug in a flash drive to iPhone, the corresponding FS plugin will be loaded, but the code of that file system has been refactored. Anyway, I can't trigger the crash of FAT or exFAT plugin, so iOS is not affected by this issue. Moreover, this is also a good exploit mitigation. You can't attack the kernel directly from file system anymore in iOS. Suppose you can successfully launch an attack. You only obtain the permissions of a normal process, but you still can't obtain the kernel permissions. Remember that vulnerability I posted on Twitter? This vulnerability has been fixed in 2019 in macOS Catalina 10.15.2 and is already a bit old. It provides the ability to read and write 32 bytes in arbitrary addresses, but the address can only be located after the XATTR info page. So it is a perfect vulnerability, and I will explain the vulnerability briefly. Function default set XATTR again. Let's take a look at this piece of code. There is a special attribute in XATTR file named Finder info. When replacing this attribute, it jumps to the following code, which allows the users to set 32 bytes of data for this attribute. The issue is that address offset of Finder info also comes from the XATTR file, and there is no check if it is a valid range. When this value is greater than 64 KB, an out of bounds occurs, and we can control all the OOB read bytes written to kernel. In fact, if you read this attribute by get XATTR syscall, you can get an out of bounds read, but it doesn't matter. The OOB write is enough for the exploitation. Unlike the previous vulnerability, this one doesn't have as many limitations. It is a perfect vulnerability, and its exploitation process is simple. You just need to lay out the memory correctly, then craft the key message and forge a larger length. Then destroy this key message, make an overfree. The overfree target is OOL port and an OS data. The OS data object serves to disclose kernel memory, and then as before, you can build a TLP0. Done. I will not discuss the details of the exploit process. You can find the exploit code in my GitHub. The link is given in the bottom left corner. About this vulnerability, there is one interesting thing. You can put a malicious XATTR file on a flash drive, then plug in this flash drive into a macOS computer, and will panic immediately, displaying a multi-language screen of death. Analyzing the crash logs, I found it was caused by getXATTR OOB read, which is probably because the Finder automatically passed the XATTR file. This could be not lead to arbitrary code execution, but it's funny. It's zero-click panic. Although few people noticed that the file system is also an effective attack surface to the kernel, this type of vulnerability does exist and is powerful, such as the ones I showed today. Therefore, when designing and implementing a file system, you need to be very careful. Any flaws in it may cause serious impacts. What's more, the meaning of XCTTR is interpreted by different programs. For example, Finder uses tags. Archive tools need to process XCTTR, and Gatekeeper also relies on XCTTR to decide something. This all involves the parsing of XCTTR, which is a new attack surface. It is possible to attack these softwares through XCTTR. Finally, on iOS, userfs is a good exploit mitigation. Thank you for watching. That's all of my talk today. You can find all the POC code on my GitHub, and you can contact me by this email. Thank you.